Hi grade 11s. Today we are going to talk about vapor pressure. So this will be lesson 1.8. No, 1.7. 1.7. You're going to be doing exercise 8, but this is lesson 1.7. Okay, so to define vapor pressure, it's a hard concept for some people to sort of get, but basically it's the pressure created by gas molecules when a liquid changes to a gas or vaporizes in a closed system. So this diagram might help here. So we've got a liquid, these are our liquids, and in a closed system, so remember closed system just means that it's got a lid on it, it's shut. We have some particles are always, and we've talked about this before, some particles are going to escape the system, right? They're going to gain enough energy to escape. Some particles are going to come back down, and if these rates of escape and the rate of recapture or the rate of evaporation versus the rate of condensation, if those are equal, we end up with a dynamic equilibrium. Now, we've got three different gases here. So this one, for example, has a lot of gas particles, right? So this would be naturally, this is a chemical property of a substance. So this particular substance here, for example, would be fairly volatile, right? So a lot of the gas particles are wanting to change into the gas phase. So we've got lots of gas particles here. So this would have a high vapor pressure, right? As compared to this one here where we have less gas particles here. So in terms of vapor pressure, this figure number 3 here would have the highest vapor pressure as compared to figure number 2. Let's not worry about figure number 1 there. Okay. Now, a substance vaporizes when it has enough energy to overcome the intermolecular forces holding the molecules within a liquid. So it's got to overcome the IMFs, because remember, IMFs want the molecules or the particles to stay close together, right? So what we know from this, a substance with strong IMFs is going to have low vapor pressure because not a lot of those particles are going to change state, right? Whereas a substance with weak IMFs will have a high vapor pressure because a lot of the particles will. So if we look here, this volatile one, these would have weak IMFs. This one would have, figure 2 here, would have strong IMFs. Now, so let's write this relationship now. So this is an inverse relationship. When we talk about if one thing goes up while another thing goes down, we would say that they're inversely related. So we can write down that IMFs vary. So this little backwards fish symbol, alpha, means varies with. So it varies with 1 over VP. VP is vapor pressure. So what this tells us is as IMFs increase, vapor pressure is going to decrease. Now we've got our kinetic energy distribution curve here. Apparently I didn't get a picture of it. All right, we're going to sketch it. So what this is, okay, we've got a bell curve shape. So this is percent of molecules here, and this is our kinetic energy along the x-axis here. So all this is very similar to our Boltzmann distributions, right? So let's pretend that we've got a beaker here, we've got a thermometer in it. So let's say that thermometer says 26 degrees Celsius. What this means, this is just showing that these top parts here, so there's not very many of them, but those little parts there, they might be at like 27 degrees Celsius or 28 degrees Celsius. The vast majority of them, right, are going to be 26 degrees Celsius, but you're always going to have some hotter particles here, or the particles with more energy. Now, only the higher energy particles have enough energy to escape at the surface of the liquid and enter the gas phase. And we've talked about that before when we discussed evaporation. So in an open system, the gas particles are going to escape. In a closed system, we get our dynamic equilibrium. And so our dynamic equilibrium, we're going to have a liquid then when we've got our evaporation. I'm just going to say evap. We've got condensation moving the other way, and this is our gas here. So this would be our dynamic equilibrium if this system was closed. The liquid is evaporating into the gas phase, and the gas is condensing into the liquid phase. So at equilibrium, the rate of evaporation is equal to the rate of condensation. Make sure you know that, okay? And this does not mean that the number of particles in each phase is equal. That is not what that's saying, okay? So just talking about the rates. Okay, now there is a relationship that exists between vapor pressure and temperature. So vapor pressure is directly related to temperature, which means if you have a low temperature, so low temp means low temperature, oops, I did it backwards, is low vapor pressure. So those are directly related there. So temperature is the only factor that's going to affect the vapor pressure of a substance, which makes sense. If you had a closed system, right? So this is our liquid particles here. That's a terrible drawing. Even I can't handle that one. Woo! There we go. Give myself some space. All right, if you have a closed system, so we've got our liquid here, so closed with a lid on it, it's got a certain number of gas particles here, right? So this would be naturally how this works. So we've got equal rates of evaporation and condensation. If you put a flame, that's a flame, looks kind of like a weird flower, but if you put a flame under that and start heating this, the particles in here, the liquid, are going to have more kinetic energy, right? And more of them are going to phase change. If I increase then the number, I'm going to change the color. So let's say the blue ones are due to the increased heat here. So if I increase this, what's going to happen to the pressure inside of there? Yeah, the vapor pressure will increase, right? So temperature is the only way for us to change the vapor pressure of something. Now, there is a relationship that exists between vapor pressure and the boiling point of a liquid. So you can just recall there, boiling point is the temperature at which a liquid changes into a gas. So we have a liquid phase changing into a gas, that's when boiling happens, right? Now, boiling occurs when the pressure pushing the particles apart. So remember, vapor pressure you can think of as a force going up. It's not a force, but I know that's physics terminology, but think of it as moving upwards. So the particles want to become a gas. There's the pressure holding it together is the atmosphere, okay? So this is vapor pressure and this is the atmospheric pressure pushing down on it. Now, when these two things are equal to each other, that is when we have boiling, okay? Or you could say when the vapor pressure is greater than the atmospheric pressure, we have boiling. So this situation here, that is when things are boiling. So I want you to keep that in your mind as we go through this. So that is me in Banff. This back when we had band trips. I know some of you were getting ripped off. You don't get your band trip. We would go to Banff. So in the mountains, the altitude causes a different atmospheric pressure because atmospheric pressure changes based on where you are on the planet relative to sea level. So I would like you to reason out what happens to the boiling point on top of a mountain. Now remember, boiling happens when the vapor pressure is equal to the atmospheric pressure. So what happens if we change the atmospheric pressure? What does that do to the boiling point? That's your question. So think about that, and then we're going to discuss that in class. Okay, now we also have calculation questions to do with this. So we're going to be reading the graph here. So we've got CHCl3, CCl4, and water. I know those are a little hard to see on the PowerPoint here. So this is a vapor pressure curve. So it's the pressure of the vapor as a function of the temperature here. So we can see that as the temperature is increasing along the x-axis, our vapor pressures are also increasing. And we've already talked about that before, how they're directly related to each other. So question number 1 here, at what temperature does the carbon tetrachloride, CCl4, boil at 80 kPa? So remember, vapor pressure and atmospheric pressure have to be equal in order for something to be boiling. So at 80 kPa, I'm going to go along here, you're going to go across until you hit CCl4. At that point, that is when the vapor pressure is equal to 80 kPa, which is equal to the 80 kPa of the atmospheric pressure. And so you're going to just drop your perpendicular here, and you're going to read it, and reading off the chart there, it's going to be around 55 degrees Celsius, okay? So on the line is boiling, okay? So make sure you know that. Under the line would not be boiling. Above it would also be boiling. Okay, next one. Which substance has the highest boiling point at 80 kPa? So which substance has the highest boiling point at 80 kPa? So again, let's find our 80 kPa, which is here. So if we move across here at the line, oh, CCl4 is boiling. Go a little higher, hotter, CCl4 is boiling. And lastly, water is boiling. And water is going to boil there. But which substance has the highest boiling point? At 80 kPa is going to be water. Next, which substance has the weakest IMFs? So remember, how were IMFs linked to vapor pressure? Do you remember? They were inversely related, right? So that means if something has weak IMFs, what do we know about its vapor pressure? It's going to be high, right? Because these are opposite. If one is low, the other one is high. So you are looking for the substance that has the highest vapor pressure. So sometimes people get a little confused reading these charts. What I do, a nice easy way of managing this is just pick a temperature that has all three curves on it. So I'm just going to pick 40 here. So which one has the highest vapor pressure? It's not going to be water, not going to be CCl4, will be the CHCl3. And that's your answer there for that one. And I know that because it's going to have the weakest IMFs because it's got the highest vapor pressure. Okay, you can try assignment, the exercise 8. Yeah, I'm going to post the answer key to this so that you have it. So check your work and make sure you're doing everything correct on that and come to class next with your questions, okay? Okay, thanks.